All right, today we're going to look at a topic that isn't super heavily tested on the AP exam, but it is a really important topic for things like engineering, if anybody goes on to be an engineer. And it's just also like economics. It's used in a bunch of different places in the real world, and I actually think it's one of my favorite topics in all of calculus, although it can be fairly difficult. So I think some people might have a hard time with some of the stuff, the setups at least, similar to when we did related rates. Although I will tell you, I used this in college way more than related rates, which came up very rarely. So we're going to start with a problem you should already be able to do. So optimization means making things be as good as they can be, whatever good means. And so let's start with a warm-up problem that you should already be able to do. What are the absolute extrema? Absolute extrema are absolute max and absolute min. So the absolute max and absolute min of this function on the domain -1 through 4, and justify your answer. So go ahead and try this. You should be able to do this from the first semester. And what we should notice here is absolute maxes and mins on a closed domain. We're going to use the extreme value theorem, which is the candidate and the candidates test. So the extreme value theorem says when we have a closed interval and a continuous function, we are guaranteed, so if we have a closed interval and a continuous function, we are guaranteed to have an absolute maximum and an absolute minimum either at the critical values or the endpoints. Those are the only places it can happen, and so those are our candidates. We can actually start by finding f of -1. Let me just make a table here. So we can start by finding the values of -1 and 4, because maybe those are the absolute maximum and minimum. So we're going to plug in -1 here and 4. So f of -1 is going to be -2 plus 3. Notice that when it's you cube a negative, it becomes still a negative, but when you square a negative times a negative is a positive. Plus 36 plus 6. So here we had a negative times a negative was a positive. So this looks like 43. So 43. We're going to plug in 4. So f of 4. This is a big number. Okay, 4 times 4 is 16, times 4 is 64, times 2 is 128. 4 times 4 is 16, times 3 is 48. 36 times 4 is 144, so minus 144 plus 6. So this is 176, 182, minus 144 is, I believe, 38. But I don't know, I might have messed that up somewhere. It's possible I put the wrong numbers there. Let's see. Now, these are two of the candidates. Maybe it's at the endpoints. That's what the extreme value theorem says, is when there's a continuous function on a closed interval. It could be at the endpoints, or it could be at the critical values. So let's find the critical values. We find the derivative. And the derivative is 6x squared plus 6x minus 36. And we want to know where is this equal to 0 so we can find the critical values. So I'm going to divide everything by 6. And factor x plus 3 times x minus 2. These multiply to make -6 and add to be 1. So x is -3 and x is 2. -3 is not between -1 and 4, so we don't need to check it. 2 is. Let's check 2. 2 times 2 cubed, so f of 2 is 16. 4 times 3 is 12. 36 times 2 is 72, and plus 6. This is definitely going to be the absolute minimum. 16 plus 12 is 28, plus 6 is 34. 34 minus 72 is -38. And so we get that the absolute minimum value is 38. So the absolute min of -38. And if we want to say where it happens, it's at x equals 2. And an absolute max of 43 at x equals -1 by the candidates test. That's our justification. And to actually have justified it, you needed to show that you found the values at these 3 points and that you found the critical value somewhere. You needed to show that you found that the derivative was equal to 0 somewhere. So we are going to take this idea of finding absolute maximums and minimums and apply it to real world situations where we want to find maximums and minimums of various things. So the question is always going to be, well, what are we finding the maximum or minimum of? Well, let's just look at what's coming. We want to maximize the area of a fence you enclosed. Okay, that seems reasonable for a farmer to want to do, is to make the biggest area of a fence they could do. We want to maximize the volume of a box. So you're trying to make a box hold as much from the same amount of material. We want to find the closest point on this curve to this point. We're minimizing the distance. We're finding the absolute minimum distance. We're going to find the least amount of material used to make some volume. This would be an important thing for business. And in fact, like this was a major thing in businesses, is to use as little material as possible to cut their costs. So they're minimizing the amount of material used to accomplish some goal. We want to find the most economical can, which means minimizing the price of the can. And here we want to have the largest area a rectangle can have. We're maximizing the area. So these are going to be some things we want to find the maximum and minimum of today. Similar to related rates, some of the setup is going to involve drawing a picture sometimes and figuring it out how to write an expression for the thing we want to minimize. Our big idea that we're going to be doing all day is we're going to write some sort of function. So like a function of x equals something, and we're going to find the endpoints and the critical values, and we're just going to find f of the endpoints and f of the critical values. We're going to do the candidates test on whatever the thing is that we are maximizing or minimizing. Let's see how that works. You own 100 feet of river property. River property means it's along a river. So here's a river. Okay. You buy 280 feet of fence to enclose a rectangular area. So there's going to be a rectangle somewhere. We have 280 feet of fence. You are only using the fence on 3 sides because the river is the 4th side of a rectangle. So it must be like a straight portion of the river. So this is one of the sides of our rectangle. And there's going to be a rectangular area. So now I feel comfortable that I can draw it. Looks something like this. It's not the best rectangle in the world, but okay. So here we've got fence, 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 and over here we have river. Okay. Now, what dimensions will maximize the area? When we talk about the dimensions of a rectangle, we're talking about length and width. So we need to choose, we'll call this the length. It doesn't matter which one's the length and the width. I'll call this one the length, and these two will be the width. And so I'm just going to think of, we want to maximize the area. So let's write an expression for the area. The area is equal to what? What's the area of a rectangle equal to? Well, it's length times width. The problem is we need to have just one variable to be able to maximize it. This has 2 variables, length and width. And so oftentimes we're going to need another expression somewhere to be able to substitute. This was a big thing in Algebra 1 when we did systems, and it's going to come up here. In this case, we need a relationship between length and width, and we're going to use the other piece of information they gave us here. There are 280 feet of fence. Okay, well, where is that fence going to go, and how does it relate to length and width? Well, here's fence, 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 and then river. So we know that if we add up the length plus the width plus the length again, that's how much fence we have. We're trying to do the maximum amount of area, so we're going to use all of the fence that we can use. And so we know we're going to use 2 lengths plus 1 width, and that will equal 280. And this allows us to solve for one of the variables. It looks way easier to solve for W here because you could just move the 2L to the other side. You could also solve for L, but you'd have to subtract W and then divide by 2, and you'd end up with fractions. Seems gross. So we're going to subtract 2L and get 280 minus 2L. And this is what W is. So we can take what W is equal to, and we can substitute it in for W. And now we'll have a function, area, that's only in one variable. Area as a function of length will be the length times 280 minus 2L. This needed to be in parentheses because it is a binomial. And let's go ahead and simplify this. I don't want to have to do like product rule stuff. So A of L, I could just leave it as A, but I'm just saying it's a function of L. Let's just call it A, whatever. A equals 280L minus 2L squared. Now, we're going to try to maximize this. The question becomes, what are the endpoints? So we know we need to find the critical values. We're going to find the derivative and find the critical values. We're also going to find the endpoints. And the endpoints can be a little tricky sometimes. What is the smallest or the biggest the length could be? Well, the length, there's two lengths and one width. And since there have to be two lengths and we only have 280 feet, even if the width like goes to 0, like even if we make it super narrow, the length is never going to get higher than 280. So this is one endpoint, or sorry, not 280, 140, because if the length is 140, 2 times 140 would be 280. And even if we add in 0, that's what's going on there. And normally we would say the other endpoint would be, what if the length was 0? So if the length was 0, then the width would be 280. But there's actually a small piece of information that I missed when I was first doing this problem. I got this wrong one year when I was doing this problem, because I said, oh, yeah, the smallest the length could be is 0, and then the width would be 280. Why can the width not be 280? How come the width is not able to be 280? Well, it's because it says in the problem that you own 100 feet of river property, and the width goes along the river. And so this cannot be more, this has to be less than 100. The width has to be less than 100. And if the width has to be less than 100, and if we put in, if like 100 is the biggest the width can be, then we can find what the smallest the length can be. So 2L plus 100 is the lowest the width could be, is 280. 2L equals 180. L equals 90. So the other endpoint is that the length equals 90. These are the endpoints of our interval, and we want to see if there's any critical values, and we're gonna check it out. Okay, so okay, go ahead and find the critical values. What are the critical values? What values of L make this equal to, make the derivative equal to 0? And hopefully you took the derivative and you found 280 minus 4L, and we want to find this where this is equal to 0. So move the 4L to the other side maybe, and divide by 4. L is 70. So we need to find the area when the length is 70. We need to find the area when the length is 90, and the area when the length is 140. So when the length is 70, what is the area going to be? Well, the area is length times width. But we already have it as a function of area. So let's do this. So we've got 70 times 280 minus 2 times 70 would be 140. And we'll get 70 times 140. Oh, wait, hold on. This critical value is outside of this. So this critical value would have been the maximum, but it is outside of our possible things. We can't have a length of 70 because then the width isn't able to be 140. So this one is out, okay? So it's outside, it's a critical value, but we can't check it because it's not within our endpoint. So the answer is going to be either this one or this one. So when the length is 90, we're going to get, oh man, I didn't give myself enough space here. I'm using this formula. When the length is 90, we'll get 90 times 280 minus 180. 2 times 90 is 180, and that's 100, which makes sense, right? When the reason this was our endpoint is because it's when the width is 100. So you get 9,000. Or the other endpoint is when the length is 140, and there we get 140 times 280 minus 140 times 2 is 280, and we get 0. This one's the absolute minimum, and this one's the absolute maximum. So we're trying to maximize the dimensions, and that's going to happen when it asks us for the dimensions. So our answer is length is 90, width is 100. when the length is 90 and the width is 100, that's when we will have the maximal area. Now, if they hadn't told us this, the maximum area would have happened at the critical value, which would have been at 70. So, weird stuff. But I hope we see how we're using the candidates test to establish endpoints, check any critical values that happen between them, and then just do the candidates test. The hardest part is setting up like what is the equation, as you're going to see in this next one. Find the maximum volume of an open top box that can be made by cutting out squares from the corners of an 8-inch by 15-inch rectangular sheet of cardboard and folding up the sides. I want you to pause for just a second and try to draw a picture of what they are talking about. You need to be able to read this and understand what is happening. And it is literally the hardest part of this problem is reading it and setting up the problem. After that, it's not too bad. So what you should have said is we're taking an 8-inch by 15-inch rectangular sheet of cardboard, and we are cutting squares from the corners and folding up the sides. So we're cutting out squares, and then I hope you can see that like this side is going to fold up, 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 and we're going to get, you know, a nice little box where, you know, it's a folded up box. So when you fold up those sides, you're going to get a box. Okay, so what is the thing we're trying to maximize here? We're trying to maximize the volume. So we need an expression of volume in only one variable. What is the volume of a rectangular prism or box? You should know that the volume is the length times the width times the height. Now there's a problem here. What is that problem? The problem is that there are 3 variables and we need only 1 variable. Okay, well, we know that the length is going to be like, okay, we can kind of see where the box is going to end up. I'm going to use red here. We're going to see that the box is going to be here, 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 and then the part that's sticking out is like this length. So it's this length all around, right? It's going to be like the height. So this distance is the height, this distance is the length, and this distance is the width. So how do we relate them to each other? Well, we're going to use the fact that we cut stuff up. I'm going to take a minute and just see if you could like set up what's going on here. You might not be able to. I'm going to call this length that we cut out x. Whatever the length of these squares is, I'm going to call x. So here's x, 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 x. We don't know what it is, but it's the same in all of these. And so now I can tell you what the length is going to be in terms of x. The length is going to be this whole side, 15, minus 2x, because we're going to cut out this x, and we're going to cut out this x. So this was 15, but we took away this and this. So it's 15 minus 2x. What is the width going to be? And hopefully we can see that the width, this length right here, is going to be this whole length, which was 8 inches. So this is 8 inches. But we took away this and this. So the width is this leftover part here. So it's 8 minus x minus x. So it's 8 minus 2x. And finally, the height is what? What is the height when we fold up this box? How is the height going to be? Well, whatever this length is, this x, that's what you're folding up. And so the height is just x. I could have just used height for these if I had wanted to, but instead I chose to substitute and make x. So the volume is going to be the length, 15 minus 2x, times the width, 8 minus 2x, times the height, which is x. And let's see. So what is I guess the question is, what's the biggest the height could be and what's the smallest the height could be? Well, the smallest the height could be is 0, right? That's one endpoint. You can't have a box that's smaller than 0. What's the most the height could be? What's the most this length I could cut out is? And it might be a little hard to see at first, but it's 4. The other height, the other endpoint is 4. Because if I cut out more than 4, there's only 8 inches here, and I have to cut out 2 heights worth to go in. Like x gets cut out in 2 places, and so 4 plus 4 would be 8. You're not going to be able to go higher than 4. I guess I should be calling this x is 0, and x is, I used x for the height. So these are the endpoints, and I need to find the critical value. So last time we saw that the critical value wasn't between these two endpoints. We're going to need to make sure that the critical value is between these endpoints. Now, I don't really want to do a triple product rule thing. I think I'm just going to multiply this out. But you could do let's do no, I'm going to multiply this out before I do the derivative. So 15 times 8 is 120, I believe. 15 times 2x is 30x minus 16x plus 4x squared, and all of that is being multiplied by x. These can combine, that's 48x, and then I'm going to also distribute the x's to everything. So we get 120x, this is 48x's times x, so 48x squared, and then 4x squared times x is 4x cubed. So here is our volume, just in one variable, and I can find the critical value very easily now. Go ahead and find the critical value here. We want to find the derivative, which is 120 minus 96x plus 12x squared, and set it equal to 0. Oh, yuck, this is ugly. This is a quadratic. I see that they're all multiples of 4. I'm going to at least divide everything by 4 first. So I'm also going to rearrange it so the 12x squared comes first. So 3x squared, this is 12x squared divided by 4. 96 divided by 4 is 24. 120 divided by 4 is 30, so plus 30 equals 0. And I need to factor this. So, I don't remember what factoring technique we used your year. There's all sorts of different factoring techniques. 3x times x, and I need, what are the ways to multiply to make 30? It's going to be minus. So we got, it's not going to be 1 times 30, 2 times 15, no. 3 times 10, no. 4, 5 times 6. 5 times 6. It's really close. Am I missing a way to multiply to make 30? 3 times 10, 2, 15. What's wrong here, guys? How do you multiply to make 30? Am I missing something? Oh, no, 2, 3, 5, 6. 6, 5. Man, I'm like the end of a long day and I'm blanking on how to factor apparently. Or maybe I made a mistake earlier and this one doesn't factor. Let me check something on the calculator to make sure I'm not like doing something wrong. So we can do the discriminant to see if this is possible to factor. This is just going to see if I made a mistake. Minus 4 times 3 times 30. The square root of that. So I made a mistake earlier. Okay, so this, oh, man, maybe this doesn't factor. Do we have to use the quadratic formula here? Maybe we have to use the quadratic formula. That seems like, oh wait, hold on, guys. Okay, so 4 times that seems right. 4 times that seems right. Where did I make a mistake, guys? Where's my mistake? Okay, let's go back up here. Did I multiply wrong? You guys are gonna get to see what happens when I make a mistake and I go looking for it. 120 minus 30 minus 16 plus 4x squared all times x. 48x, good. This is right. I could have also divided by 3 here. This is, these are all factors of 8. Are they all factors of 8? Something's wrong. Are they all factors of 12? Boy, what did I do here, guys? 4, 24, 3x squared. Where did I go wrong? Well, let's make sure I'm not like reading the problem wrong. Okay, 8 inches, 15 inches, 8 minus 2x, 15 minus 2x. That seems right. X is the height. That seems right. It's 15 times 8. Is that 120? Yes. Minus 16x minus 30x plus 4x squared. Oh, my goodness. And here it is. 30 minus 16 is not 48. It is 46. And now I cannot divide this by 4. Because when I multiply by 2, it's... Oh, it is 92. I can divide by 4. I could have divided by 12 there. So now I can divide by 4. And I get... Man, that was so ugly. It took me so long to find that mistake. So 30 minus... Now this is 23x plus 24x squared. Sorry, plus... we divided by 4 plus 3x squared. I don't know why I didn't write the x squared first here. I'm going to rewrite it. 3x squared minus 23x plus 30. And so it's the same thing as before. I was just, it's going to be the one that I said was really close. So 3x and x, and it's going to be minus 6 minus 5 is how this factors. So I can see that x equals 6 is a critical value, and x equals 5/3. X equals 6 is outside of my endpoints, and so I'm not going to consider that one. But x equals 5/3 is inside. So let's find the volume when the height is 0. Well, we can see very quickly that when the height is 0, the volume is going 0 times anything is 0. We can see very quickly that when the height is 4, 8 minus 2 times 4 is 8 minus 8 will be 0. And so that will be 0 also. It's going to definitely be the critical value. So the critical value is when x is 5/3. And it said find the maximum volume. Guys, I know by the candidates test, it just has to be this answer. I don't want to multiply this stuff out. I'm just going to leave it as 15 minus 10/3. I'm just multiplying 2 times 5/3 times 8 minus 2 times 5/3 is 10/3 times 5/3. This has to be the right volume, and I don't want to mess around with all these fractions right now. I could. I guess maybe I should. I don't want to. I will. Okay, fine. This is 45/3 minus 10/3 is 35/3 times this is 8 is 24/3 minus 10/3 is 14/3 and times 5/3. This is just so ugly. I wonder if this was on the calculator section or non-calculator section. You can just leave it like this. I could have left it at a bunch of other places. Yuck. 70, 490. I don't even know, guys. What is this? 2, 7. I don't really want to multiply all this out. I'm trying to like multiply it a fancy way in my head. It's like 490 times 5. Okay, 490 times 5. I think. 0, 5, 4, 2450. 2450 27ths, whatever that is. That's the maximum volume. Yeah, I should have left it here. All right. Cool, guys. Wow. This is when math goes wrong. All right. Find the points on the curve of y equals square root of x that is closest to the point 4, 0. Try to draw a picture of what is happening. And now we'd like to figure out what it is we're minimizing, or what it is we're optimizing. So hopefully we know the square root of x looks like this, right? It's got points at 1, 1, 4, 2, and we're looking for the minimum distance. What's the closest point to 4, 0? So like, what line can I draw here that will be the minimum distance? Geez. Okay, well, I know I'm drawing a line here to this curve, and I want this distance to be as little as possible. So the thing, I want to minimize my distance. And so hopefully from your geometry days, the distance is setting off alarm bells for what we can do here. The way we find the distance between two things is it is the square root of y2 minus y1 squared plus x2 minus x1 squared, because it's just like, hey, look, we're taking the distance between these two things, so it's a Pythagorean theorem thing. It's you subtract the two x's and square it, you subtract the two y's and square it, it's a squared plus b squared equals c squared, and so this distance will equal a squared plus b squared equals c squared, and so we can take the square root to actually find it So we want to minimize this. Now, what is y2 and y1? Well, one of our things is just a point, 4, 0. So I'm going to call this x1, y1. And our other point is going to be x, comma, y, but we don't know what x and y are. But we know that y is the square root of x, so it's x comma the square root of x, like it's to just one variable. So the distance between this point and this function is the square root of y2, so which is square root of x, minus y1, which is 0, squared, plus x2, which is x, minus 4 squared. We want to minimize this distance. It's the distance between a point and a curve, okay? And you guys can see the setups here are tricky. There's also a cool trick you can use, which is that if you're minimizing something, you can also just minimize the square of that thing. Like whatever minimizes this will also minimize the square root of this. So I'm gonna like actually call my variable the distance squared, because it'll get rid of the square root, because I'm just going to minimize, so x, square root of x minus 0 is square root of x, square root of x squared is just x. This is what I am minimizing. I'm just going to minimize it, because if this is minimized, then the square root of it will be minimized. It's an increasing function, and so this will minimize it. So we didn't talk about the endpoints. What is the lowest x could be? So endpoints, what is the lowest x could be for this function? Well, we're looking for what point on the curve, and this curve ends at x equals 0. Square root functions begin when x equals 0. And what's the maximum x? Well, there are two ways to think about it. You can think of it as infinity, or you could say like, hey, look, I know after x equals 4, the x and the y are both going to keep getting bigger and bigger because it's going up and getting further away. And so it's not unreasonable to think of 4 as the endpoint, or you could think of it as not having an endpoint and just having infinity and seeing what happens there. But I hope you guys, well, we'll see that in a second. I hope you guys can see if you plug in infinity, like for x, this is just the distance is gonna keep getting longer and longer and longer. So like if you're trying to minimize the distance, this is not good. So 4 is like the last thing that maybe is the closest, because after that, both the x and the y get larger. Before 4, the y is getting larger, but the x is getting smaller because you're getting closer and closer to like right above it. Okay, what about the critical values? What are the critical values here? Well, the derivative is going to be 1 plus, I'm just going to do a chain rule thing here. This is 2 times x minus 4 times the derivative of the inside, which is just 1. So this is 1 plus 2x minus 8. It also would have been completely reasonable to square this first. So do like x plus squaring a binomial, you square the first one, multiply these two together and double it, and then square the last one, and then take the derivative of this more simplified version. Either way, you'll end up with the derivative is 2x minus 7. And so where is that equal to 0? Well, you add 7 and divide by 2, and so we get 7 halves. So x is 7 halves, so 3.5. So let's find the distance at each of these places. The distance at when x equals 0 at this endpoint, what is the distance between here and the point 4, 0? Well, the distance is 4, right? So the distance at 0 is 4. It's 4 away, 1, 2, 3, 4. What about the distance when x is 4? When x is 4, the y value is 2. And it's obviously exactly 2 away, so that's better. And that should make sense that it's closer. But we also need the distance at 3.5. This is a little bit annoying. So let's see. The distance is going to be the square root of 3.5 plus 0.5 squared. So square root of 3.5 plus 0.25, square root of 3.75. But I know this is the right answer, and the reason I know it's the right answer is because square root of 4 is 2, and So square root of 3.75 is a little bit less than 2. And so the square root of 3.75 is the answer. That is the minimal distance. I think this was a calculator section, so like I think you could have done like square root of 3.75 and been okay with it, and seen that that was a little bit less than 2. Oh, but it didn't ask what was the minimal distance. It said find the point on the curve that is closest to 4, 0. So the point on the curve was when x was 0, when x was 3.5. So when x was 3.5, the y value is the other part of a point. The y value is square root of 3.5. So when we plug in x is 3.5, the y value is square root of 3.5. And that is the point on the curve that is closest. These are pretty difficult questions we're doing today, guys. You don't need to feel bad if you struggled on these. I clearly struggled on at least one of them. Maybe more. Maybe I've made more mistakes. I don't know. I want you guys to try to read this yourself and try to set up a picture and set up as much math on your own as you can on this problem. So read it, set it up on your own, and only unpause the video after you've tried it yourself. You may not get very far. You may get all the way through it, but you need to try it to then see where you're having trouble. Okay, let's do it together. A company is packaging their candles in containers with square bases and open tops. Okay, so square bases. So I'm going to call this x and x because it's the same length because it's a square. And then there's open tops. I don't know, something like this. So here's the top and it's open. Okay. And we want to find, these containers must have a volume of 32 cubic inches. Find the dimensions that require the least amount of material. So the volume is going to be, volume is length times width times height. But in this case, the length and the width are both the same. So it's x squared times height. That's the volume. And we know that needs to equal 32. But that's not the thing we are minimizing. The least amount of material. We're going to be minimizing the amount of material used. So what is the amount of material that is being used here? Well, it's how much surface area is on the bottoms and the sides, but not the top. So the base is x and x, square base. So the surface area that we are minimizing is x squared. That's the base, right? When there's x and x or whatever, whichever one the base is, I don't know. And then there is going to be 4 sides, all of which have a length of x and a height of h. So it's going to be 4 times x times h, because this rectangle is going to have a base of x and a height of h. We don't know what those are. What's the problem with this here? Why can't we just minimize this right now? Well, we have 2 variables. We have x and h. So we're going to need to use our relationship from before, where we found that the volume, which is 32, this is our constraint. I'm going to solve for h because it seems easier. It's 32 over x squared. And so I'm going to plug in 32 over x squared here for h. So this is x squared plus 4x times 32 over x squared. And now we have a function that's just of x, the surface area in terms of x, which was the length of the base. So x squared plus, we can multiply, this is 128 over x. One of the x's cancels out. So if you multiply by x, you can cancel one of them out. Great, so let's think about our endpoints. So endpoints for x, so x is this length of the base. What is the smallest x could be? Well, x could be 0, right? So x can't be smaller than 0. Is there a largest x can be? No, but I guess if we we're trying to, so the largest x point is infinity, but this is gonna be wrong because imagine making a giant box. Is this gonna use the least amount of material? That's definitely not the answer. This is not what we want. We want x to be fairly small because we're trying to use the least amount of material possible. So yeah, you could make a giant box that's barely any height at all, but that's not gonna help you. So x equals 0 is gonna have to be So it's like this teensy tiny like thing that's like super tall, and that's not going to be the answer either. It's going to be wherever the critical value is. So we really just need to find the critical value here. So the derivative is going to be 2x. This is power rule. This is 128x to the negative 1. So we multiply by the power, so minus 128, and we lower the power by 1, so it's going to be x to the negative 2, so over x squared. And we need to find the critical value, which is where this is equal to 0. So we've got x squared in the denominator. We're going to multiply both sides by x squared. So 2x cubed minus 128 equals 0. Move the 128 to the other side and divide by 2. So 128 divided by 2 is 64, and the cube root of both sides to undo cubing, x is 4. So x equals 4 will make there be the least amount of material. I know that because when x equals 0, this needs to be infinitely tall. That's infinite material. And if x gets like really big, then how is that going to help you have the least amount of material? It's got to be just x equals 4. What are the dimensions? Well, it's going to be 4 by 4 because the bottoms are 4. And if it's 4 by 4, this needs to, it said it needed to hold a volume of 32. So 4 times 4 is 16 times what gives me 32 times by 2. 4 by 4 by 2. That is the volume. That's the dimensions. This is how we write dimensions. This is like length by width by height. So that's the answer to the question. That's the dimensions that require the least amount of material. Okay. Notice that I just want to point out that the open top meant there was only one bottom that was x squared. If the top had been closed, it would have been 2x squared would have been the volume of the total surface area, because it would have been an x squared on the bottom and an x squared on the top, but instead it was just only 1x squared because there was an open top. Whew, guys, I suspect very few of you got that right on your own, and that's okay. It doesn't mean you're like bad at calculus or bad at math. These are just like really tough problems. But I hope you're starting to at least like see some common parts, and you'll get more and more comfortable about it as you do it. A cylindrical can is to hold 20 pi meters. Oh, go ahead and try this on your own. Get as far as you can on your own. Pause it, read it, try it on your own, and then unpause it when you're ready. A cylindrical can is to hold 20 pi meters cubed. The material, so there's a cylindrical can. So a cylinder is when there is a base that is a circle and a top that is circle, and it goes down at a right angle. So there's a cylindrical, it's what a can looks like, okay? And it's to hold 20 pi meters cubed. This is a volume because it's in meters cubed. So volume. The material for the top and the bottom costs $10 per meter squared. What is this meter squared? This is area. So they're talking about the surface area. How much area we have is going to be how much we have to pay. And the material for the sides, so like all of this stuff around the sides, is $8 per meter squared. Again, it's talking about the surface area. We want the most economical can. That's the cheapest. We want to minimize the cost. So we want to minimize the cost. What's the minimum value of the cost of the can? So let's write an equation for the cost of the can. So the cost is going to be the cost of the bottom plus the cost of the side, bottom and top. Okay, so the bottom, the way we find it is it's $10 per meter squared. And how do we find the area of the bottom? Well, the area of a circle, we need, it already told us we have R and H here. So this is R, this is H. The area of the bottom is pi R squared. And that's going to get multiplied by 10, right? And there's also a top here, and it's also pi R squared. So it's going to be 2 times pi R squared times 10, so 20 pi R squared. Okay. What about the cost of the side? How do you find the outside of a cylinder? This goes back to your geometry. And we should know that the way you find it is you just find the circumference of a circle and multiply it times the height. Because that takes, it's like if you do circles all the way up, you end up with like the surface area. So it's the circumference of a circle times the height. So it is 2 pi r, that's the circumference of the circle, times the height. And then this answer, this area, is going to be multiplied by $8 per meter squared. So I should have put this up here. This is so embarrassing. So 20 pi r squared plus 16 pi r h. Our problem here, of course, is that we have two variables. We have r and h. So we need a relationship between them where I can substitute one of them. I hope we can see where that's going to come from. It's going to come from this 20 pi that it says the volume is. The volume of a cylinder is, you take the circle at the bottom and just multiply it times the height. So pi r squared h, that'll fill up the whole volume, pi r squared h. And that needs to equal 20 pi. So I can solve, h is the easiest variable to solve for. I'm just going to divide by pi r squared and cancel out the pi's. So it's 20 over r squared. 20 over r squared. So I'm going to substitute in this equation. I'm going to say c, just as a function of r, is going to be 20 pi r squared plus 16 pi r times h's 20 over r squared. So we can simplify a little bit. So 20 pi r squared, 16 times 20 is 320 pi, and one of the r's is going to cancel out, so pi over r. So, okay, what is the smallest the radius could be? Well, if the radius is 0, it's going to need to be like infinitely high, so that's not good. If the radius is infinitely big, there's no like biggest, that's going to use way too much material too, and so we want whatever the critical value is. That's going to be the only minimum. So we need to find the critical value, which means finding the derivative. So 40 pi r. Here, this is r to the -1 power, so we're going to multiply by -1 and lower the power by 1, so it's going to be over r squared. It's r to the -2 power, and this is going to be equal to 0. And this is very similar to solving the one up above. So hopefully we can do it. We multiply both sides by r squared to get rid of the r squared in the denominator. So 40 pi r cubed minus 320 pi equals 0. We're going to move one of these to the other side. I'm going to do this one. Equals 320 pi. So we add 320 pi to both sides. Let's solve for r. We divide by 40 pi. So r cubed equals, the pi's will cancel out. 320 divided by 40 is just 8. So the cube root of 8, we do the cube root of both sides, is 2. So r is 2, and it's time to find the radius and the height. The height is 20 divided by the radius squared. So 20 divided by 2 squared. 2 squared is 4. 20 divided by 4 is 5. That is the cheapest can you can make. You can see how this is like important for business and engineering when you're building things. Like, how do you make things the best they can be for what you want? But it is difficult to set it up sometimes. All right, last one, guys. Last one. Again, pause it. Just take a few minutes until you get stuck to try it on your own. You can pause it at various points when you get unstuck. A rectangle has a base on the x-axis. Okay, so I guess we're going like this. So there's a rectangle. And its upper two vertices, oh my gosh, are on the parabola y equals 12 minus x squared. So this is negative x squared plus 12. So it's a parabola that has a vertex at 0, 12. And is concave down, looks like this. Okay, so there's this parabola, and it says there's a rectangle that has its upper vertices on that parabola that has its base on the x-axis. So it has to look like this. So there's some kind of rectangle. Mine kind of looks like a square, which maybe is the answer. I don't know. Okay, what is the largest area this rectangle can have, and what are its dimensions? Okay, so we need to find the area of this rectangle, and the area of a rectangle is equal to the length times the width. Okay, so here's the length, here's the width, or whatever. Doesn't matter which one's which. Now, I guess what I need to do is relate this parabola somehow to it. So I need to get this into one variable. So I need to use this parabola. And I'm thinking about, like, what is this point? This point is x comma So x would be like this distance. This is x. And the y value then would be 12 minus x squared, because that's what it says y is. Y is 12 minus x squared. And so this is the height, is 12 minus x squared. And the width is going to be not x, because it's from here to here, right? Or I guess I called this the length. It's going to be 2x. So the length, so if I call this length x, then I can see that the height of the rectangle is going to be 12 minus x squared, and the width of the rectangle is going to be 2x's. So the area of the rectangle is 2x times 12 minus x squared. Length times width is this, and I got it in just one variable. So what's the smallest x could be? Well, the smallest x can be is 0, right? So the smallest x can be is 0. That's one of my endpoints. And the biggest x can be is whatever this is, whatever this width is, like where it would hit this. But it's not going to be the answer. It's not going to, like, I don't know, it's something less than 4, obviously. It's some irrational number. It's like, where is 12 minus x squared equal to 0? So x squared equals 12. X is the square root of 12, which is like 3 point something. Okay, so 3 point something. I don't know what the 3 point something is. Okay, so our x has to be somewhere between 0 and 3 point something. And our critical value, the derivative, I guess I should rewrite this by simplifying so I don't have to do the product rule. This is going to be 24x minus 2x cubed. You could have done the product rule and it would have been just fine. The derivative is 24 minus 6x squared, and I want to set that equal to 0. 24 equals x squared, divide by 6. Take the square root on both sides. X is 2. We only really care about the positive value. Sure, x could be negative 2, and that's this point over here. But there we go. So x equals 2. So what are the dimensions? If we end up making a rectangle that has x of 0, then you have a length of 12 and a width of 0. That rectangle has a area of 0. If the width is, if you use x is the square root of 12, then you'll end up with a rectangle with a length of square root of 12, or 2 times the square root of 12, and a height of 0, which is also an area of 0. So this is definitely going to be the answer. So when x is 2, we want to find what the length and the width are. So when x is 2, the width is going to be 4, and the height is going to be 12 minus 2 squared. So 12 minus 4 is 8. And so the area of that rectangle is 4 times 8, which is 32. Guys, this was a tough day. You do not need to feel bad if you struggled on every single one of these problems. It is worth practicing things that are hard sometimes, not because I expect problems are going to necessarily, there might be a problem on the AP exam that's as hard as one of these. These are this would be about as hard as any problem on the AP exam would be. And when they write problems that are hard like this, they mostly just expect that you do a couple of things. Like, hey, if you're able to get any points on it, you did great. So you don't need to feel bad if you struggled on some of these ones. I think you'll see in your homework there's some slightly more manageable ones that you can maybe sink your teeth into. But the big idea is we write an expression for whatever we're doing, and then we try to minimize or maximize by using the extreme value theorem. Again, do not feel discouraged if this was very hard, which I suspect it was for almost everybody. It's worth practicing and struggling with hard things sometimes, and that's what today was. So good luck on the rest of your homework. I think you'll find that it'll start getting easier and easier as you continue to practice it. Feel free to ask me for help if you need it. Maybe have a good rest of your day.